Welcome to Math 105, Chapter 8.5, Normal Distribution. So what we're going to be doing is now probabilities of continuous random variables. So something that we haven't quite reached yet. We're going to be using not so much Desmos. We're still going to be using our TI-83s or 84s if you have them. I'm sure Desmos can do it. Again, not something that I am super comfortable with yet. Now, we did talk a little bit about different shapes of these probability curves. A normal bell-shaped, you're going to be seeing that here, but now with your histogram, and we're going to transfer that into now a continuous random variable and how that can work for us. So given that the histogram over on the left-hand side, notice that each of the bar is how many units wide. Well, in our case, they're going to be 1 unit wide each and all the way up to 10. So let's see, let's write that down first before I get ahead of myself. Therefore, if we're looking at the probability between your values of 3 and 5, right, like normal probabilities, we're going to be adding up all of the areas of your rectangles, the area using your height of each rectangle. So if we are interested in these ones in darker green, right, we're going to be figuring out, well, these are the rectangles that they're interested in. And if we're looking at the area of a rectangle, we're doing base times height, your base being 1 unit wide. So we're really interested in the height. So to the best of your ability, can you estimate the height of each of these bars? Well, perhaps this first one is 0.12, and then maybe this one is 0.21, and then maybe this one is 0.24. We're going to add them up as we suggested for the ones over here. 0.12 plus 0.21 plus 0.24 to make 0.75. So our probability of those rectangles combined would be about 57%. And that would kind of make sense because these are much larger portions of your graph, much larger rectangles, so we should have a bigger probability. Now, if we added up all of these values, though, again, our values in this case, they didn't tell us too much for context, so we can assume that it stops after 10 and it starts at 0. So if we were to add up all of these probabilities, wink, wink, what do they all total to? Well, if we added them all up, we would have a total of 1 or 100%. Now, with the histogram, we have values within an interval, which means that we're going to be dealing with a continuous random variable. We've been working a lot with a finite random variable or discrete random variable, things that are countable. But now we're going to be talking about intervals, things that are not so easily countable. So, and it can range over a much diverse value, right? So a height of an athlete, temperature of Charleston, it definitely fluctuates a lot more than what we're used to. So continuous variables can take on any real value whatsoever. So all real numbers, right? Think about that, what that means, like any real number. So note in chapter 7, we were talking about finite probabilities, the set of outcomes like a dice roll or poker cards, etc. Whereas continuous variables need an interval. Heights of our classmates, we go through growth spurts, we're getting older. It fluctuates over a much larger range, which means when we calculate your probability, it's going to look a lot different than what we're used to. Now, we do have to get used to the notion of a probability density function. So keep in mind, all the area underneath the curve should total to 1 or 100% because it still is a probability. If we are looking for a range of probabilities, we're just going to be looking for those specific values to add up. Now, in order to be a normal density function or a normal distributions are symmetric and bell-shaped. We did get exposure to that with the empirical rule back in chapter 8.4. So symmetric meaning they look the same on either side and you have that bell curve aspect to it. Now there is an error on your notes, and that comes where it says standard normal, and it's suggesting that this graph right here is standard normal, which it's not, and we're going to take a look as to why that is. So standard normal means that you have a mean of 0 and a standard deviation of 1. And for our graphs, we're going to assume that the numbers that are showing on your x value is going to suggest on either side, if you can find the middle, that on either side, that's going to be your standard deviation. So let's start off with this graph. Is it symmetric? Yes, it's symmetric. Is it bell-shaped? Well, yes, it's bell-shaped. Now, is it a standard normal graph? Standard normal meaning you have a mean of 0 and a standard deviation of 1. Well, your mean is at 0, but what's your standard deviation on either side? Your standard deviation is on 2 on either side. So is this considered a standard normal graph? No, it is not standard normal. So yes, symmetric. Yes, bell-shaped. Yes, the mean is 0. No, standard deviation is 2. So it should be 1. So if this is not considered a standard normal and just a normal graph, normal bell shape, of these two, is there one that is considered standard normal? Yes, so this one right here has a mean of 0. The other one has a mean of 2. This one has a standard deviation of 1. And this one also has a standard deviation of 1. However, it does not have a standard, it does not have your mean at 0. So this one is considered still normal. Well, this one is considered standard normal. So it has all of the qualifications, including your standard deviation. Now, why are we making such a big deal that things are in standard normal form? Well, in order to be standard normal, it's a lot easier to calculate because you're starting at 0 and then on either side, you're just ticking up by 1. So if we were to look at your standard normal graphs, we can calculate your probability very quickly using this table. Now, this is called a Z table. It's called a Z table because now all of your values are not in your standard like X variable. We've now transformed it into Z, Z being your standard normal variable. And we'll write that here. You're going to be seeing Z equals and X equals. Z is your standard normal variable. And this one is considered just your normal variable. All right, the difference between standard and just normal, we talked about just a moment ago. So standard, we need mean of 0, standard deviation of 1. Okay, Now there are a bunch of Z tables out there. Ours specifically is going to always start at your mean and then go up to your X or up to your value. And that would be the in-between value is your probability that you're looking for. So in order to read your Z table, first thing we're going to do is just a couple tests. So let's say I wanted to calculate 2.30, or the probability, and I'll write it like this. The probability that Z is, let's see, how did we want to structure it? Oh, we'll do it like this. We'll do it like this. Z is 0 less than or equal to, Z is less than or equal to 2.30. We'll do something like that. So it's an easier transition. So as long as we know that they're always going to be starting at 0, right? We can ignore this 0 value. The probability of 0, as you see right here, is 0. So instead, we're going to go up to our value, ours being 2.30. Now there's a quick form right here. If we're looking for 2.30, we're always going to be starting with your first two values. Your first two, we're going to be looking at the column down below. So once you locate your column here, then we're going to go over to the very next value, 0. 0 being this decimal place, the hundredths place. Now, when you lock that down, we're going to be finding the overlap. So the overlapping portion is your percentage, is your probability. So the probability that Z is between 0 and 2.30 is 0.4893. Let's try it again with the probability that Z is between 0 and, let's say, 2.53. So again, ignoring the 0, let's look up here, 2.53. So locating on your column first, 2.5, and then going over to the third decimal place, or sorry, not the third, the second decimal place here. So this tells us the row, and then this tells us where to stop. So again, we are at 4943. Now let's go away from this smaller version and let's tackle it on a big one. Let's try it with the probability of 0 is less than or equal to Z, which is less than or equal to, let's do 0.08. And again, we're going to do one more, or maybe a few more. Z less than or equal to 1.27. Now on these ones, I will show you a better like picture form of it, and I can do that for the remainder too. So let's see, 0.08. So looking up here, 0.0, we're looking for 0.08. I'll like keep that reference here. So 0.0 is located here, which means I'm now looking for the 8 up here in my row, which is over here. I'm looking at that overlap, which is now 0.039. 0.039. Now if, oops, 0. I left one decimal place off, 0.319. Okay. Now, if I were to draw a quick picture, this is just our standard graph probability, or sorry, your mean is 0, and we're going all the way up to 0.08. So that just means our shaded portion here is 0.039. Or ours from before, if I were to scooch this down just a wee bit, scooch it down. The one before it right? Much larger probability. So it's going to encompass a lot more area. So again, your mean is 0. We got 2.35. So this probability here is 0.493 or 4943. So let's try it one more time with 0 to 1.27. So now our reference, we'll move this over a little bit. We said is 1.27. So let's start off with your first 2 in a 1. So 1.2. So 1.2, we're going to trail all the way down until we see 1.2, which is right here. So we're going to be in this row. Now we're looking at the 7. So this row here, and then we're going to look to where we see a 7 all the way over here. So that's your 7, and we're going to scroll down until we meet up. 7 here, we said it is going to be right there, 3980. 3980. So again, a quick little picture. 1.27. This is what we found here as your probability. Okay, so now let's have you do a few on your own using a z-table. So you got a couple variations for you. So at least try the first 2 on your own. I'm hoping at this point that I don't need to go back and flash the z-table, and we can assume that we're able to read it. I will show you a quicker way as well if you're interested, but that'll come a little bit later in our video. So 2.4, and we're looking for the probability that we're between these values. 0.24. So I'll just do it for one more. So 2.4 is right here, and following that 2.4 was nothing, so a 0. So we're working with this first one, 4918. 4918. All right, let's try it again one more time now with a 4.3. It should be just slightly larger. And I'm hoping you get 0.4925. Now, let's take a look at this variation. Now, what is the hang up here? Well, not only are we now seeing not a 0 on this side, but we're also seeing a negative. Does our z-table have a negative? No, all of our values are positive. So what are we doing? Why did I throw this on there, right? So one thing we can assume, because it's a symmetrical graph, so a very symmetrical graph, what happens on one side of the graph happens on the other side. So that means if I have a negative 1.37, and I'm looking for this probability, because it's symmetrical, I can use the positive half of the graph as its equivalent. So if I look for 1.37 on my positive side, 1.3 and all the way to 7, 0.1447, or sorry, 4147. So if this is 0.4147, we can assume that even when it's the negative side, that this is going to be 0.4147 also. Because it's symmetrical. So because symmetric, the probability of the positive is equal to the probability of the negative number. So for us, we actually already determined the negative probability of it, or the negative value. Not that the probability is negative. Our probability should never be negative. So we have here as 0.4147, which means we need 2.43. And I'll do that in green. So then what are we going to do with these two probabilities? Because we already calculated 243 as the one before it. 0.4925, that was the one from previously. So what does it look like we're going to have to do with those probabilities? Well, it looks like we're going to have to add them to make 0.9072 or 90.72. So if you haven't paused the video on that one, I would like you to pause the video and try it out one more time now with this particular one. All right, so let's look for this probability right here, negative 2.39. Again, we're looking for the positive value of it, and then we're just going to take that same probability. I'm hoping you came up with 0.4916. And then let's do it again for 0.65, something a little bit smaller. This one being 0.2422. Again, we can add them together because they are on opposite sides of the mean. Okay. Now let's look at this variation. So we're going from this first one of 0.21. Again, your Z tables always start with 0, and we're going to go all the way up to 0.21. And I'm actually going to erase that value because we really want the probability between 0.21 and 1.6. So this is what we are interested in. We would like this value. So our first step that we have to do, as always, is calculate your probability of that first one. So from 0 to 0.21. So let's go ahead and get that probability, because your Z tables always go from 0 to that value. Now this will give us 0.0832. And if we were to do it one more time with your next value, let's do that one more time. Not the best looking graph, but oh well, 1.6. So if we were to do it again, right here, this gives us 0.4452. Why did I make it so squishy? Let me try that one more time. Okay, so we got this part here where we have 0.4452. Okay, now keep in mind, we have seen a number of different problems where we might have something being double counted. So if I were to overlay this, right, trying to line it up as best I can, there you see 0, and there you see a little bit of the green and maybe none of the pink. And if I were to move it down, right, there's going to be a small overlapping portion, right? What has been double counted in the green section? Well, notice that the pink, because these are the exact same graphs as best I could make it, there's a small overlap, right? It just means that a part of that green also entails the 0.21 amount. So that pinkish part is found within it. So in order to get between these two values, right, we overinflated by a certain probability. We overinflated by exactly 0.0832 amount. So that means when we go to talk about your probability, when they're on the same side, we're going to subtract out the smaller of the two values. So we're going to take 0.4452 minus 0.0832 to get 0.3620. Okay, take out that double counted amount, always the smaller value, if it's on the positive half, that is. So that being said, pause the video, see if you can try this one on your own. So in our case, we have this value here, 1.37. Over here, we have 2.43. So that in pink, actually, this is the probability that we want. So 1.37, if I were to make this graph over again, we'll just save that graph, copy. 1.37. This pink part, we have already calculated now to be 0.4147. And one more time. 0 and 2.43. This green part, which has a little bit of overlap in it. We said this is 0.4925. So we're going to subtract these two values out. 4925 minus 0.4147, 0.0778. And there you go. Okay. So these are all if we have standard normal curves. So what are we going to do if it's not a standard normal? Instead, it's just normal, right? So we actually have to standardize. So if we're looking at these two graphs here, one being your standard normal, which has a mean of 0, and then to either side is your standard deviation. On this graph, your mean obviously is not 0, and your standard deviation to either side is not 1. So we're going to transform this graph into this graph where we can use a z-table. So we have to do this by converting your values, your A and your B values, that range, kind of like we did up here, right? These range of values to be now standardized. We have to force them onto the z-table. We do that by taking your A or your B, or A and your B values, and subtracting by your mean and dividing by your standard deviation. What that does is now force these values into a z value. So you don't have to do this again. You only have to subtract it once and divide it once. So now these values are on your table. These values are on z-table. I'm actually going to do that. Okay, so you only need to subtract your mean and your standard deviation one time. By no means do you have to do it twice. Okay, just once is enough. So this says pressure gauges are manufactured by precision core must be checked for accuracy before being placed on the market. To test the gauge, the workers use it to measure the pressure of the sample of compressed air known to be at a pressure of exactly 50 pounds per square inch. So they're telling us that your mean is 50. They also tell us that in a minute as well. So it says if the gauge reading is off by more than 0.1 or about 0.5 pounds, it is rejected. So I'm going to write that down. Reject if off by 0.5 pounds. Assuming that the reading of a pressure gauge under these circumstances is a normal variable with mean of 50 and standard deviation. Oh, I wrote the wrong variable. In standard deviation of 0.4, find the percent of gauges that are rejected. So we have some mean right here as 50, right? And we want to know, well, what will be rejected, right? What probability, what percentage will be rejected? So these rejecting amount would be over here. If it's within the area, we're going to reject. So I will write that a little bit more clearly. This is the rejection. So that is the area of rejection. Now we are told that we have a standard deviation of 0.4, but let's figure out, well, what are your values to reject? Keep in mind, we're going to reject if we're off by if we're off by 0.5 pounds. That means to either side of your mean, what would be the rejection margin? Well, if we add or subtract by 0.5, that would get us to those margins. So about 50.5 or about 49.5 would be the values at which we could reject. So the inside is okay, the outside is not okay. Which means since these values here that you're seeing are not found on your z-table, we now need to go from this normal graph into a standard normal where you have a mean of 0 and a standard deviation of 1 to either side. So we want to know, again, the same graph, same rejection area, but now using z values. So we're going to take your values here. We're going to put them into that small equation. So we have the probability of 49.5 is less than or equal to x, which is less than or equal to 50.5. Because they don't fit on your z-table, we're going to force them onto your z-table. We said we're going to take 49.5, we're going to subtract it by your mean, and divide it by your standard deviation. We're going to do this again to the other side. 50.5 minus your mean divided by your standard deviation. We place that into your calculator, we get negative 1.25 is less than or equal to z, which is less than or equal to 1.25. And it's okay that these are the same value. It's because on either side, they were off by the same margin. So on your Z table, let's find these two values, 1.25, the negative half, and 1.25. Now in your table, we don't have that negative, but that's okay. We're still getting the positive values of it. Now this in green is the amount by which it is okay. We're not going to reject. So from 0 to negative 1.25, hopefully you found it was, well, actually, let me do the other half. From 0 to 1.25, we should have found 0.3944. But because your Z table is a symmetrical curve, we're going to actually use that same value because it's the exact same number. Now, this would be the percentage, if we added them together, that these would not be rejected. This is not rejected. Now, is that the amount that we actually need? No, we want to know the percent of gauges that are going to be rejected. So what are we going to do with your probability? Well, if all probabilities add to 100% or 1, then we are going to take this value and subtract that out. 1 minus 7888 to give us 0.2112. This would be the percent by which our gauges are rejected. Now, we can do that by hand or we can do it by calculator. And I'll show you, maybe I'll just do it right here. So let's see the calculator aspect. So we're going to hit the following buttons. Second, vars, normal, CDF. Normal CDF is cumulative. Cumulative meaning we want a range of them, right? Think about what it means to be a cumulative final. And we want the lower value, the upper value, the mean, and standard deviation. So on your table here, vars is located right next to the cleared button on the right-hand side. So we're going to hit second vars. And notice that there's normal PDF and normal CDF. PDF is for a specific point. CDF is going to be that cumulative aspect. We're going to go and hit enter. If you have a newer calculator, it tells you what you need to enter in. The older ones, it doesn't. So you're going to have to remember it. So it says lower bound. It just means the lower number. So we have negative. Now for your negative, make sure you're using the negative button and not the minus button, which is located right between enter and your decimal place. 1.25, comma, your comma is located right above the 7. Your upper value is 1.25. Oh, so sorry. I'm actually using the Z values, which you can use your Z values if you want to. You can also use this for a Z table, or let's actually put in your actual non-Z values. So 49.5, comma, 50.5, comma, your mean of 50 and your standard deviation of 0.4. Close your parentheses. Oh, and I noticed I just did an error. 0.4. Go ahead and hit enter. Now notice that this is the value that we calculated before. That was an okay margin, and we wanted the opposite, so we can subtract by that. And you can always recall it and hit second enter, or because we on our Z table have 4 decimal places, we're just going to type that value in again. And notice it's off by a little bit. WebAssign should be able to accept your answers. Okay. Let's see. We had said, so we can actually use that for any sort of Z table or X table that we're going to be using. So feel free to use that calculator. So it says, what happens when you're in a specific amount of K standard deviation? So keep in mind, we're still working with your normal density curve. So within 1 standard deviation or 2 standard deviation, we still want to recall your standard normal, your empirical rule. Now this one is just slightly different. This is for your probability density rule. It's just encompassing, it's more of a percentage, but we're still going to be using your Z table here. So that being said, let's see if you can pause the video and at least attempt the first few questions. It says SAT scores are normally distributed with a mean of 500 and a standard deviation of 100. So we're looking at this value here is 500, standard deviation of 100. So find the probability that a randomly chosen test taker will score between a 450 and a 550. So we want to know this area right here. Okay. So on your calculators, we said we're going to type in second vars, CDF, your lower value. Come on, calculator. Your lower value we said was 450, comma. The upper value was 550, comma. Your mean, 500. Your standard deviation of 100. Close your parentheses. And there we have 0.3829. And I'll write that one more time. Second vars, normal, CDF, 450, 550, 500, and 100. Or you can still convert it into your Z table as well. So now let's find the probability that a randomly chosen test taker will score a 650 or higher. So we still have the same context, so 500, standard deviation 100. Now we're looking at 650 or higher. So we want this amount right here. Okay, so there's one of two things that we can do, right? So we can still use our Z table and whatever, like that's not our big thing, right? However, our graphs, right, when we're looking at your probability, we're usually going from your value here all the way up to 650, right? So one thing we can do is as normal CDF. So we can go as your Z table we normally read from your mean, whatever it is, to this value, right? So from 500 to 650, 500, and then 100, right? As normal. We would get out 0.4332. Now what this part is reading is this part right here. So if you plug that into your calculator, this is 0.4332. Is this what we want? No, right? We want a very specific portion here. So what are we going to have to do to 0.4332? We're definitely going to have to subtract it out, but by what number? It's actually not going to be one being 100%. Notice that our small portion is only how much of your graph, right? If we're looking for this portion of your graph, we have about 50% of this graph if we go from 500, your mean, to this value. So in that case, we would subtract 50 from your answer, right? 50 being half of your graph. That would give us 0.0668. So that would be our blue portion that we're looking for. So that is one way we can calculate it. The other way, right? There's two ways we could have done it. Instead of subtracting by half your graph, we could have calculated this whole thing, right? So we could have punched in normal CDF. 650 is our upper limit, 500 and 100. So that part doesn't change. Let me give myself just a little bit more room. Okay, so that part's the same, right? But what would be our lower limit here? Well, we don't exactly know how high we can go on this specific test, but can we go as low as a certain score? We can always go from 0. Perhaps they didn't even take the test. They didn't even show up. Who knows, right? I don't know what circumstance, but we can always go from 0 to that value. If we were to draw it out, 650 here, your mean here, we bypass your mean, we're going from here. So we could get all of this value here instead. That would be 0.9332. So in that case, notice that we have the majority of our graph. So now we can subtract 1 minus 0.9332 to again get 0.0668 for this part in blue. Now for our very last one. It says, what score would place you into the top 5% of test takers? Okay, so 5% of test takers. So what we don't know, or sorry, we know your mean. We know your standard deviation. We know your percentage. Top 5% would be about here. Top 5% is here. Actually, let me erase that part and I'll show it right here. This being 5% or 0.05. And we want to know, well, what is our score? What does your score have to be? Well, in that case, we're going to have to go in reverse. So instead, right, we have your probability. So, and how your probabilities work, right? We go from your 0 margin and we have to tick up to a certain value. So we need to figure out, well, if this is what percent we have and we need, well, what percent do we have for the remaining portion of your graph? Right here. Because with your inverses, right, to go opposite, we don't have this value. We don't have this score. We don't have this percentage. Instead, we have this portion here from 0 all the way up to this score. Now, what percent would that contain? So that contains 95% or 0.95% of your data. So if we can use that to our advantage, then we're going to put it into your calculator. So we're going to do second vars in your inverse normal. This says the area from 0 to that value, your lowest to your highest. Your area is a percentage. So from the lowest, 0 to the highest. Oops, I don't know how to get rid of that. So the area, comma, your mean, and your standard deviation. Hopefully I can figure out how to get that away. Okay. So let's try to do it. Inverse normal. We're not going to use your 5%. Instead, we're going to use the 95 because we go from your smallest value 0 all the way up. So we have 95 or 9.95% already, 500, and then 100. Let's see that in action. So second vars, inverse normal, 0.95, comma, 500, comma, 100. Close your parentheses. And there you got 66.6, or sorry, 66.4. So about, if we were to round, you could say maybe 65, depending on what you run it to round to. So about 66, or sorry, 664, goodness, would be your score to get you into the top 5%. Now try it again, but this time with the bottom 20. So pause and go. Let's see, bottom 20, if I were to draw a graph, I can definitely do it better. Bottom 20, somewhere around here. Again, we don't know that score. And this time, because we're working with the bottom margin, this is actually what we can use. We can use this 20%. We have that 20% or 0.2. So if we were to put that back into your inverse normal, we can use 0.2, your 500, and your 100 to get a score of 416. And there you go. That's it. Use your calculator as much or as little as you want. We're going to be doing this, if not this exact problem, a very similar problem to this on your Excel sheet. So please, please, please write as much as you can for your notes here.